So we are going to start group theory, one of the most interesting and easy courses of mathematics. So like other courses, we start with group theory by studying set theory. Set theory, as you know, very important and very relevant and very fundamental in topology, real analysis, algebra, and other courses of mathematics. So we are going to start with set theory. And the book we will follow will be Group Theory by Z.R Bhatti. And the first chapter of this book is set functions and binary operations. And the first topic of this book is set and its elements. So we'll start by this. So what is set? Very most famous, thing in mathematics is set. So set is simply collection of well-defined and distinct objects. So it means set is a collection of things in which over things are the things we are including in that collection are defined very well. It means if I am talking about this set of sofa set, if I have a sofa set, then I cannot put a teacup in it because it is a collection of sofas. Similarly, I cannot put a teacup in a furniture set. Similarly, I cannot put a bed in a teacup tea set. So these are all examples of set. By well-defined, we do not means defined well only, but we also mean that the collection of the set should not be, ambiguous. There is no ambiguity in that. We are very clear and very, about that, that we are talking about which type of objects and which type of collection we are talking about. So very important thing. Okay, and object and that distinct and well-defined objects in our sets are called elements of the set. These sets oftentimes denoted by capital letters, like A, B, X, and Y, and etc. Similarly, the elements of the set oftentimes represented by small letters, denoted by small letters, like A, B, X, and Y, and etc. And this set, as you know, enclosed by curly brackets like this, right? And if I have a set, let's say X, and having the elements of A, B, and C, and I want to say A is the element of X, or if I want to say that A belongs to the collection of things in set A, then I will write it as A belongs to set X. If F is any element and it does not belongs to X, then I will write it as, right? So this is a very important thing. Okay, if we have a set A and P of X is any statement true for A, true for A, then will be written as X is an element defined as X belongs to A such that P of X. What does mean by this? I can explain it like this. If I am talking about the natural numbers, but X such that X are less than 10. It means I am talking about all the natural numbers less than 10. It means in this, example, we have f of X as all the natural number which is less than 2. It is a statement, right? Okay, right. So there are three ways of writing sets or, representation of sets. Number one is over very famous descriptive way. Number two is over tabular form. Number 5 is over very important set builder notation. Don't worry, we'll explain it further. If I want to say that math students in a class, math students in a college, it means I am talking about all the math students in college. It means it is the collection of students. So this is the way of writing the set like this is over descriptive way, right? And over tabular form is of the form if we write the element is like this 1, 2, 3, 4, 5, and 10. This is the way of writing the collection of first 10 natural numbers is of the form tabular form. And similarly, I can write first 10 natural numbers as like this X such that x is natural numbers between 1 and 10. So this is our set builder notation, right? I hope you all understand all these forms. So this is the most essential, and but I am missing something, which is this. If set having no element called empty set. If we have a set having no element, called it empty set. If we have a set having only one element, if we have a set and having only one element, then called singleton set. Right? So this is the map of or all the essential information about set and its elements. You can take the screenshot of it, and for the students, good news is that you can now download the lecture notes of this video in the description box. The link is there. So our next topic is subsets. The first thing you should know about it is part of set. It is not different concept than set. All the rules and applications and everything of sets I am written here are all applicable to this one as well. So it is a part of set. If we have a set A, if set A is a subset of B, then written as A is a subset of B, and A contains always less than or equal to number of elements in B. It means the A contains always less than or equal to the number of elements in B. A cannot contain more elements than B. Otherwise, it will not be a subset. It will become a superset. So A is a subset of B, and B is super subset of A. Then you can also say that B contains A. B contains A. As you can see that the number of elements in, you can see that by example. If I have a set A, which is 1, 2, 3, and I have a set B, which is 3, 4. Oh, sorry. If I set it, you have a 1, 2, 3, and 4. You can clearly say all the elements of A is also in B. So A is a subset of B, and B is a super subset of A, and B contains A, right? Exactly. If this is written, then it means that A is not a subset of B. It means B do not contain A, right? Exactly. So we have two subsets. Okay. Always remember that empty set and set itself is always subset of a set, set. It means every set is a subset of itself, and empty set is a subset of every set, right? And how many subset of a set exist, you can find it by this formula: A to power n, and here n is number of elements in set. For example, in the above set, we have set A. So set A is over 1, 2, 3. So we can find its subset like this. So firstly, we can find how many subset of a exist. So 2 power 3, because 3 elements are there, it means 8 subset of A exist. So what are that subsets? For example, firstly, I elaborate above that empty set and set itself is a subset of everything. So we write empty set and whole set firstly, and other sets. 1 is a subset of 8, 2 is a subset of 8, and 3 is a subset of 8, and 1, 2 is a subset of 8, and 2, 3 is a subset of 8, and 1, 3 is a subset of 8. 1, 3 is a subset of. Do we have find all the 8 subset of it? You can count it. So in this way, you can find all the subset of a set, right? And how many subset exist? You can find this via this formula, right? So this is, I think so, I have elaborated all the essential information of it. You can take now the screenshot it. Otherwise, the lecture notes will be available in the description box. So our next topic is equal sets. Two sets, if we have two sets, if set A and set B are equal, then it means A is a subset of B and B is a subset of A. This implies that A is equal to C. So what is the condition we need to prove that two sets are equal? We have to prove that one set is a subset of other and other set is a subset of first one, right? So this is the way to represent it, right? If we have two set, A is a subset of B and B is not a subset of A, then A and B is not equal. Always remember that to prove equality between two sets, we have to prove that one is a subset of other and other is a subset of first one, right? It's very important information, right? It is not all, its concept itself is very important, but it is also applicable in different problems as well. So very careful about it. So our next topic is difference of two sets. So how to find the difference of two sets? If we have two sets, A and B, and their difference is A minus B. In A minus B, we are talking about all the elements which belongs to A but not belongs to B, right? Set of those elements in A but not in B, you can also write it like this: A minus B, X is any element such that X belongs to A but X does not belongs to B. For example, if I have a set A is equal to 1, 2, 3 and I have a set B is equal to 1, 2, 4 and then A minus B is all those elements which are in A but not in B, then 3 is the only element which is in A but not in B. So in this way, we can find the difference of it. I hope you can understand the actual meaning of it, right? So our next topic is complement of a set. So how we can take the complement of a set like this: if B is a subset of A, then A minus B is said to be complement of A. And it is often written as A complement. Yes, if I was set like this, B is equal to 2, 3, 4, 5 and A is equal to 2, 3, then you clearly see that, we have 2, 3, 5, 6, 7, right? You clearly see that B is a subset of A. Then the B complement, then A complement will be like this. A complement will be like this: A minus B. Then A minus B, the elements which are in A but not in B are over 6 is the only element. So in this way, we can find the complement of it, right? I hope you can understand it by this example, right? I hope you can understand it. Okay, our next topic is union of two sets. If we have two sets, how we can find the union of them? Union means इकट्ठा करना, together, unity. Exactly. If I have two sets A and B, then union of A and B means all those X such that X belongs to A or X belongs to B. Then I am talking about all the elements of A and B. If I write all the elements of A and B together, then I can find the union of it. You can also understand it by this example. If I have a set 1, 2, 3, and if I have a set B, which is 3, 4, 5, then the union of A, B will be 1, 2, 3, 4, and 5. This is a union. I have written all the elements which belongs to set A or set belongs to set B. So in this way, you can find the union of it. Our next topic is the intersection of two sets. Intersection means common of two sets. Simply, a definition of it as two sets A and B, then their intersection will be A intersection B, right? It is clear that the intersection of the two sets is a subset of both the sets, right? In the set builder notation, it will be written as A union B X such that X belongs to A and X belongs to B. We can also understand it by this example. This is our example 1, 2, 3, and then we can find the intersection like this. Then means I'm talking about all those elements that are both in A and B. Then 3 is the only element in A and B. So the intersection of set A and B is set. So 3 is the only element which is the intersection of two sets. So in this way, you can understand the intersection of two sets. Next topic is disjoint set. It is opposite of intersection, because in intersection we take the common part of two sets, right? Like this common part of two sets. So disjoint set, two sets are said to be disjoint if they do not have any common part. If they do not have anything common between them, anything common. You can also think of this like this. It means if we have two sets A and B, then the intersection will be empty set, right? The intersection of two sets is intersection because they do not have anything common in between them. The intersection is common. For example, if I have a set A, which is 1, 2, 3, my writing is very bad, but you have to be very patient with that. And over set B is 4 and 5. And then you have to find the intersection of them. Then it will be over empty set because nothing is common in between them, right? So empty set. Our next topic is very important, very interesting, which is index family of sets. So in our layman language, it is a collection of sets. In this topic, we are talking about a lot of set, family of sets, collection of set, classes of set, right? If given a set, if given a, oh my God, if given a set I, then for each alpha belongs to I, there exists a set. Right? And this, for example, if I write it as A alpha, then A alpha such that alpha belongs to I. So this is all the sets, right? We just plug in the value of I means alpha in it, and we get different set A1, A2, A3, A4, and a lot of things, right? And we can take the union and intersection. So we can take the union of index family of set, and we can also take the intersection of it. So we can take the union of them like this. Union alpha belongs to I. A alpha is equal to A alpha such that alpha belongs to I. Similarly, we can take the intersection of them like this. These are the very important things we have to note that. Otherwise, the notes are given in the description box. So this is all information, I think. So you should know about index family of sets. Our next set is universal set. Remember that if all the under consideration sets are assumed to be the set of a single fixed set. For example, not example, you can feel it that every set is a subset of any set. For example, if I have a set, A is equal to 1, 2, 3, then it is a set, but it is a set of natural numbers, right? Similarly, if I have a set this, then it is also a subset of whole numbers. So every set, you can take any set which comes to your mind, and you can see that it is a subset of any set in a world, right? So always remember that if we are, and if we have the set that is in your brain, you are talking about it is a subset of any other set in the set, and all the consideration set to the set you are talking about is a subset of any set, and that fixed set is called the universal set. You can think of it like biggest set of all. And all these sets are subset of it, right? And oftentimes represented by U, right? While taking the complement, union and intersection, it is assumed that it is there is some universal set with respect to which we perform this operation. So we need this universal set while taking intersections, complements, and union, right? These are all the operations of set. So we need this set, universal set to perform operations on set, right? Our next topic is De Morgan's law. Very important, very famous law. There are two laws, De Morgan's, which is A union B complement is equal to A intersection B. Similarly, the second De Morgan law is if A intersection B's complement is equal to A union, A complement union B complement. We can easily prove it. If I take the right hand side of it, I can prove this law, and you can similarly prove the other one, right? So if A the complement, it means we are talking about X such that X does not belongs to, as you know, the complement is there, X is not, does not belong to A B union, right? X such that X do not belongs to A intersection reverse, and X do not belongs to B, right? Exactly. If X does not belongs to A, then it means X belongs to A complement. Similarly, if X does not belongs to A B, then X must belongs to B complement, right? So by this, X belongs to A intersection B complement. So we can write it here, A complement. So by taking this side, we proved it, right? So in this way, you can prove the other one as well. So it is a very simple and very interesting and very important proof in group theory, and oftentimes it comes in exams. Our next topic is Cartesian product of sets. So how to take the Cartesian product? Cartesian product is like to take the product of two sets. In this process, actually, we are multiplying the sets. We are multiplying the sets. Okay. In this, Cartesian product, we get order pairs AB, which belongs to R relation. So, how to take this, Cartesian product? Firstly, we need to have two non-empty set. We take two non-empty set, two sets, A and B. So, written as A cross B, we get A, B such that A belongs to A and comma लिख लेते हैं, and B belongs to B, right? So example is if A is equal to 1, 2 and B is equal to AB, then A cross B will be written as 1, 2 and 2B, and I like to write it more clearly, and 2A and 2B. So these are all the in this way we have taken the Cartesian product of A. We relate the first element of A, set A, to the first element of B in first order pair, and second we take the first element of set A and relate to the second element of the set B. Similarly, we take the second element of set A and relate to first element of set B, and similarly we relate the second element of set A and relate it to the second element of set B. So in this way we can take take the Cartesian product, and in the end we get the order pairs like this, and this is our Cartesian product, right? So our next topic is oftentimes called binary relation. It is also called binary relations. It is the subset of Cartesian product. In our last example, we find the Cartesian product of two sets. If I take any subset of this, for example, R1, I will write any subset of this. If I take this, then it is a relation, right? So it is a relation. You can find it like this. So it is a subset of Cartesian product written as this: A relation R, subset of A cross P, right? Okay. And it is a relation if any Cartesian product, any ordered pair belongs to R, it means A and B are related to each other, and you can also write it as this. It means A is related to B. If not, then written as A, B does not belongs to A, and also written as A is not related to B, right? Exactly. Okay. If there is no relation between two sets, if relation from set A to B is empty, then called empty relation. Is empty, then called empty relation. Then called empty relation, right? You can also take, and before that, you should know that if A and B belongs to relation, then the first element of every ordered pair in relation is called the domain of relation, such that A belongs to A such that A B belongs to relation. Okay, every A belongs to A such that A B belongs to R. Similarly, the range or codomain of a relation is the second element of every order pair in it. So B in order pair belong to R is called the range of the relation. Very important, right? Okay. Now you can take the complement of a relation. Complement of a relation. Complement of a relation like this. If you have a relation, okay, R cross R is a Cartesian product, and you minus the R from it, then you can take the complement of relation, right? Okay. Our next topic is identity relation. Identity relation are the relation on any set in which the elements are mirror of each other, are mirror of each other, in which elements are mirror of each other. Okay, if on any set in which the elements are mirror of each other only, so we take only that elements in the identity relation which are mirror of each other. For example, if I have a relation, then this is our identity relation, because you can see that every element of the ordered pair, first the first and the second element of the ordered pair is related to each other. In other words, they are the mirror of each other. You can see that similar element is related to each other, like 2 is related to 2, for example, then 3 is related to 3. So all the relation of this type are the example of identity relation. Our next topic is reflexive, inverse of the relation. So how take the inverse of the relation? Okay, so the inverse of the relation will be represented by R1 R inverse will be AB such that AB belongs to R. If we make the domain of our relation, the range and the range of our relation as range, as the domain. Range we make domain range and range domain, then we get the inverse relation. For example, if we have a relation like this 1 1 2 1 and 1 3. This is our relation. Then inverse of the relation will be 1 will be remain the same, but 1 2 becomes 2 1. Sorry, 2 1 becomes 1 2 and 3 1. So in this way we get the inverse of the relation, right? So this is a very, we make domain of R, range of R inverse, and domain of R inverse is equal to the range of R, in which we make this, right? Okay. Our next topic is very similar to reflexive relation, but there's a difference in reflexive relation and identity relation. Always remember that reflexive relation reflexive relation contains identity relation. It's not itself a identity relation, but it contains identity relation. Contains the identity relation. For example, if I have a relation R, which is 1 1, which is 1 2, and which is 2 2, and this is a reflexive relation. This is an example of a reflexive relation because it contains identity relation, right? It contains identity relation and other relations as well, right? But in identity relation, you have to take only the mirror images. You have to take only mirror elements. But in reflexive relation, you can you take the mirror images while the other images as well, in which 1 1 and 1 1 is related to 1 1 is related to 1, but 2 is related to 2, but in this relation 1 is related to 2 as well. I hope you understand the concept of it, right? Our next topic is symmetric relation. Symmetric relation is a relation in which R is equal to R inverse. It is a relation in which the relation is equal to the inverse of that. For example, in which you can also write it, if A, B belongs to the relation, then if symmetric relation में, and then B, A also belongs to R inverse, then B, A also belongs to relation for all A B belongs to relation, right? What does mean by it? For example, if I have a set 1 2 3 and I take a relation on it like this, we have 1 1, we have 2 2, and we have 1 2, and we have 2 1. So this is an example of our symmetric relation. Always remember that before describing this example. Always remember that identity relation is always reflexive, symmetric, as well as transitive. If you want to check a relation whether it is reflexive or transitive, so always remember that the identity relation is all the relation. It is the reflexive as well, it is the symmetric, it is the transitive as well. So this is our symmetric relation, this is our symmetric relation, and 1 2 is there and 2 2 is there. You can verify it like this. If you take the inverse of it, so 1 1 remains the same, 2 2 remains the same, at 1 2 it becomes 2 1, and 2 1 becomes 1 2. You can also see that R is equal to R inverse. So this is our symmetric relation, right? Okay, our next relation is transitive relation. Transitive relation is very interesting relation because it says that if A, B belongs to the relation and B, C belongs to the relation, then A, C also belongs to the relation. For all A, B, C belongs to R. So we take the example of it. If if 1, 2, 3 is any set and we take the relation on it like this, 1, 1, 3, 3, and 2, 3, 3, 2, and 1, 2, and 2, 1, and that is all. So this is our example of our symmetric relation. How it is symmetric relation, we can verify it like this. If we take the first order pair, and first order pair of 1, 1 is, in this last slide, I have told that identity relation is the always symmetric, transitive, and reflexive. So we cannot check it because it is our satisfy our symmetric relation. Similarly, it is also a symmetric relation. The problems comes is the 2, 3 belongs to the relation, and 2, 3, sorry, 3, 2 belongs to the relation, and 2, 3 belongs to the relation. A, B, and B, C belongs to the relation. We can now check that is 3, 3, 3, 3 belongs to the relation. Yes, 3, 3 is belongs to the relation. Then it means over 4, all 4 satisfy the conditions for symmetric relation. Now, 1, 2, and 2, 1 belongs to the relation. It means 1, 1 also belongs to the relation. It means it is over transitive relation because it satisfies the essential properties of the transitive relation, right? Okay, our next topic is, next type of relation is anti-symmetric relation. It is anti-symmetric relation. As you can, in symmetric relation, we have to prove that A is equal to A inverse. But in anti-symmetric relation, we have to prove that if we take the intersection of relation R and the inverse of the relation, then we get the identity element. Okay, it means that if A B belongs to the relation and B A belongs to the relation, then A is equal to B and B is equal to A and B is equal to A, right? So we can understand it by example like this. If we have a set this 1, 2, 3 and we take a relation on it like this, relation R is equal to 1, 1, 1, 1, which is a very written 1, 1, 2, 2, and 1, 2, and 2, 3. So this is our relation. Then inverse of the relation will be written as 1, 1 remains the same, 2, 2 remains the same, but 2, 1, 2 becomes 2, 1, and 2, 3 becomes 3, 2. Right? If we take the intersection of A and A inverse, then we will get intersection of them. We get 1, 1, and we get 2, 2 only. Right? Okay, we have moved to next slide, which is our identity relation, right? We get identity relation, right? You can see that by example, right? We have to take a relation on a set A and we take the inverse of it, but when we intersect them, we'll get in the end the identity relation, right? Is it clear to everyone? Well done. Our next topic is, if you understand all the previous 3 types of relation, then it is very easy for you. Then it will be a piece of cake for you. It is a relation which is reflexive, which is transitive, as well as which is symmetric. It is a kind of relation which satisfies all the properties of reflexive relation, transitive relation, and symmetric relation, right? Our next topic is equivalence class. Always remember that equivalence class exists only for equivalence relation. You can only find the equivalence class of equivalence relation. If you have an equivalence relation and then the set of those elements of A, then set of those element of A, those elements which are related to a fixed, which are related to fixed element, which are related to fixed element A. Element A. And we are find the class of A, right? In which we can also write as class of A as class of A, or it's oftentimes written as class of A is a set of B belongs to A such that A is related to B belongs to R. We take all the order pair in which A is related to any other element of a set. right? Okay. Okay. Partition of the set. The partition of the set is also exist of a collection of subset. Collection of subset. We need collection of subsets. Collection of subsets. Subsets. Then there exists partition if we take the one set and taking the intersection it with other set, then we get empty set. If we collection we have a collection of subset and we take two subsets from that collection and take the intersection of them, then we get empty set. It means we have a partition of sets. Similarly, always remember that if we take the union of our index sets of A alpha, then we get in a partition, we get the whole set. It means if we take the sum of all the subsets of A alpha, where alpha belongs to I, then in the end we take take all the sets union of all the subsets of A alpha, then we get in the end the whole set A. And if we take any two subsets from the collection A alpha, then we get the empty set in partition of sets, right? Is it clear to everyone till now? So till now we have covered all the basics of sets, subsets, relations, and now we are going to start functions. Very important functions, and try to elaborate function as quickly as I can. I know all of you know these basics of set theory, but we have to skimming through it. So what is function? Function is a subset of unique subset of relation, unique type of relations. Remember that in function, for all x belongs to x, there exist unique y belongs to y. Always remember that x is the domain of a function, while y is the range of the function. Range or codomain of a function. And our function is f of x is equal to y. Okay, then always remember that function works like a machine. Function works like a machine. Like a machine. We give input and get output, right? And always remember, very important, very important. Every function is a relation. Every function is a relation, but every relation is not a function. But every relation is not a function. And at the same time, always remember that every mapping is a function. Because function and mapping is same thing. Every mapping is a function. Right? So this is a very important points about functions. Okay. Then, okay. We can write it as, okay, in functions, we get in mapping, right mapping, we get images of a function. We get images. We get images. Right? We get images. Get images, right? So this is all the essential information about function. Okay. The first type of a function is constant function. A function whose domain, a function whose range is fixed. No matter what's the input. What's the input? The function remains the same. So it means f of x is equal to c, right? Okay. The graph of this function is a straight line, right? where straight line C, right? We have a x-axis and we have x-axis and we have a 0, right? Graph is a state function. Okay, right? But in which domain range of a function is fixed. Range is fixed. Domain is not fixed. Not fixed, right? So this is our constant function. Our next topic is the type of function which is surjective function, oftentimes called onto function. We will later discuss the extension of the function, inshallah, right? So our next topic is onto function. In onto function, you have to remember the only thing is that surjective function or onto function over range and domain is equal to each other. It means the codomain of a function, is equal to the range of the function. Right? This is a surjective function, right? If the range R of a mapping xy is the set y, then the set f is a mapping of x onto y. Such a mapping is called surjective mapping. So if you have any relation, then you have to then you want to know about it is whether it is onto or not. Then always remember check only one thing: is the function having domain is equal to range, then it is onto function. You have do not worry about any other things. Always remember this thing, which is very important, that the domain of function is equal to range of the function. Only thing I have to I try to make the things easier for you. So we will remains to the basic. Don't try to involve too many things. So injective function oftentimes called one-to-one mapping. We have one-to-one function, one-to-one mapping, in which for x, every element of x, every x belongs to x have distinct image in y belongs to y. For example, like this, A, B, C, and then we have 1, 2, 3, then 1 related to 1. This is our function from x to y, right? Distinct images, right? This is our distinct. And our next example is bijective mapping. Bijective mapping that is both one-to-one and onto, one-to-one and onto. It is a type of mapping. It is that type of mapping which satisfies both the conditions for one-to-one and onto. Means every element in X have distinct image in Y, and the range of the function should be equal to the codomain. Then it is over bijective mapping. Okay, the inverse of a function. Okay, if we make domain, range, and range domain, domain, range, and the range of a function to make domain, right? If we have a function f which maps x to y, then inverse of a function will be map x to y, right? So like this, if we have a set 1, 2, 3, and we have a set, I have written very badly, so try to make better example, 1, 2, 3, and if we have 4, 5, and 6, which is related to each other like this, which is a function f, then f inverse will be like this: 4, 5, 6 related to 1, 2, 3. This is our inverse function. You can easily see that the domain of first function becomes the range of the second function, right? So in this case, our domain, this is our range, and this is our domain, and this is our range, right? So this is our inverse function. Composite functions, composition of a function. In this, we compose functions. If we have two functions like f of x, which relates x to y, and we have g of x which relate y to z, then f of z will be, then over g of x kar lete hain. Okay, then over g of x will be x to z, right? For example, if I have a set f of x is equal to x square and our g of x is equal to 2x, then g of f will be written as g of f will be okay, g f of, actually we put the in place of value of x in the g, the function f of x like this. So we want to find this. We have a g of x is equal to 2 as it is, and in place of x we put the function f of x. Then we get 2x square, which is the value of our g of x. So in this way we can put the composition of function, right? Okay, I hope this is clear to everyone. And then we move to our next, which is binary relation, right? Binary relation, binary operations. Binary operations, always remember it is also mapping. It is also a mapping or a rule or a function. The domain of this function is this function is Cartesian product of set, and range of this function is set x itself. It means it is represented by steric, and oftentimes steric is a mapping such that the Cartesian product is the domain of the function and the range of the function is the set x itself, right? Okay. And it is written as, in the Cartesian product, we get the order pair. As you know that order pair xy belongs to x cross x. Then it means that A steric A, in which this is the binary operation we defined on the elements, right? So always remember, binary operation satisfies the Collier property, associative property. Associative property is the property of this. Like this property, and also satisfy the cumulative property, closure property, associative and cumulative property. Means that A steric B is equal to B steric A, B steric A, which is over, and identity element also exist. Identity element exists, and the inverse element also exists, and inverse of the element also exists. So this is all from today's lecture. I hope this all is clear to everyone. Today we have not solved too many examples, but rather than we focus on the examples, on the concepts and the points on it. You should note it on your registers and neat copy. In our next lectures, we will define a group and solve too many examples of it. So do not worry about that. Till that, Allah Hafiz to everyone. Don't forget to subscribe our YouTube channel and watch all the videos. The lecture notes is available in the description box, as well as our playlist link is also available. So Allah Hafiz to everyone.